So, let us resume our discussion on the balanced sliding window protocol. So, we are looking at a protocol where we want the following properties to be proven, namely that we require safe delivery, that is, in every reachable configuration of the protocol, the words that are copied into the out P array are actually the words that were there in the in P array, and we also need eventual delivery, that is, for every integer k greater than or equal to 0, we want to reach a configuration with sp greater than or equal to k and sq greater than or equal to k. Okay. Now, because this holds for every integer, it means that the protocol must make progress all the time. Now, we saw that in the protocol what we essentially did was that we have a chosen window from which we are sending packets, and the window can slide forward only when we have certain packets which have been received, right. So, the two processes P and Q are somewhat lockstepped in that in terms of the progress that they can make without receiving the packets from the other side. We showed that the following protocol invariant holds for the protocol, and now we want to formally prove that this invariant actually implies that the safe and eventual delivery requirements are satisfied by the protocol. Okay. Now, let us look at the invariant once again. In the invariant, we have no, give this one there also. Yes. So, we want to see here that there are 8 different clauses in this, right, and I have numbered them as 0p, 0q, 1p, 1q, 2p, 2q, and 3p, 3q. Okay. We will start with by proving the first one, that is, we will try to show that the safe delivery is guaranteed. Okay. To see that the safe delivery is guaranteed, we first look at 0p and 2p, and we claim that 0p and 2p together implies that out p 0 through sp minus 1 is equal to in q 0 through sp minus 1. Why? Because for all I less than sp, that is, for all I between 0 through sp minus 1, 0p gives us that out pi is undefined, is not undefined, right, and then what does 2p gives us? That if it is not undefined, then that is equal to, then out pi is equal to in qi, right. So, that means that for all I from 0 through sp minus 1, out pi is equal to in qi. Okay. So, this takes care of the safe delivery requirement, that is, we have shown that the protocol invariant guarantees that this. How did the invariant actually guarantee this? Because the invariant itself takes care that the protocol only copies in pi into pack wi, sends it to the q side, and that pack wi is copied into out qi. So, that way we make sure that it is the right word which is copied into the packet and then back into the final out array of the destination, right. So, it is simple, this is not a complicated thing at all. The more tricky thing to prove is the proof that there will be eventual delivery. To prove that eventual delivery will occur, we must first prove that the protocol will not deadlock, that is, at every point of time we will always have a non-zero window of delivery, which means that there will always be some packets which can be transmitted. Okay. So, to prove that, we will first prove this lemma. This lemma which says that the protocol invariant P implies SP minus LQ is less than equal to SQ is less than equal to AP plus LP, AQ plus LP, and is less than equal to SP plus LP. Okay. We will understand shortly why we need this lemma, but once we prove this lemma, it will be very easy to prove that the protocol will not deadlock. Okay. Now, again, to prove this, we will use this invariant. So, to prove this part, namely that SP minus LQ is less than or equal to oh, I have missed one thing here. There is less than or equal to AP less than or equal to this. Okay. Let me do one thing. Let me rewrite this thing once, so that there is no ambiguity in this. What we want to show, the lemma, is that P implies SP minus LQ is less than or equal to AP is less than or equal to SQ is less than or equal to AQ plus LP, which is less than or equal to SP plus LP. I missed out one of these inequalities in the last slide. Okay. Now, let us see how we go about proving this. So, let us start by proving this inequality first, right. Now, look at the invariant. In the invariant, if we look at 0p and 2p, okay, what does it give us? It says that we have from 2p AP is greater than I minus LQ, right, and what is the maximum value that this I can take such that it is not undefined? SP minus 1, right. So, if you put that here, then you will see that you get this inequality, right, that you get SP minus LQ is less than or equal to AP. Okay. Then let us look at the next one, that AP less than or equal to SQ, this one. Okay. But AP less than or equal to SQ is already here, AP is less than or equal to SQ, right. So, that inequality is also taken care of. Then again let us look at the next one, namely that SQ is less than or equal to AQ plus LP. Okay. Now, for doing this, we look at 0Q and 2Q. Okay. If you look at 0Q and 2Q and apply the same reasoning, then you will get, so if you put SQ here, then SQ actually, what is the maximum value that I can take here? SQ minus 1, right. So, if you put that here, then you will see that you get this, that SQ is less than or equal to AP AQ plus LP, right. So, that takes care of this one, and then we are just left with the last one, that is AQ plus LP is less than or equal to SP plus LP. Okay. That follows from 3Q, because in 3Q you have AQ less than or equal to SP. So, if you add LP on both sides, then you get this is less than or equal to SP plus LP, right, and that is what we want here. Okay. So, now we have proved that this whole sequence of inequalities hold. Now, what we want to show is that at any point of time there will always be some packet which can be sent. to show that, we first go by the definition of the protocol, that as LP plus LQ is greater than 0, which as I said in the beginning is a restriction, that both of them cannot be 0. So, LP plus LQ must be greater than 0, okay, and both remember are positive numbers, they cannot be negative. Then at least one of these inequalities is strict. That is, we have less than equal to, less than equal to, less than equal to, less than equal to, but you cannot have all of them to be equal to, because if all of them are equal to, then you will end up with SP minus LQ is equal to SP plus LP. Okay. That means LP plus LQ equal to 0, but that is not the case. So, therefore, at least one of these inequalities will have to be strict inequality, right. Now this cannot be the case. So, one of them has to be a strict inequality. If one of them is a strict inequality, then we can claim that SQ less than SP plus LP or SP less than SQ plus LQ. Why? See, if at least one of these inequalities is strict, let us look at this point. Okay, this one will either be strictly less than this, or this one will be strictly less than this, because if both are equal, if SP minus LQ is equal to SQ and SQ is equal to SP minus SP plus LP, then we will again have equality, which cannot be the case. So, it must be the fact that either this SP minus LQ is less than SQ, which is this, SP is less than SQ plus LQ, or SQ is less than SP plus LP, which is this. Okay, right. Now, what we have from P, that is P also implies AP less than or equal to SQ and AQ less than or equal to SP. Okay. These were 3P and 3Q. Okay. So, if we have these two, then from this it follows that AP is less than or equal to SQ is less than SP plus LP this one, or AQ less than or equal to SP less than SQ plus LQ. Now, what does this tell us? This tells us that at any point of time, either this must be true or this must be true, right. If this is true, then P can send the packet indexed SQ. Why? Because it falls in the window of sending. What is the window of sending for packet for P? P can send all packets I such that AP is less than or equal to I less than SP plus LP. That was the window of sending for P, and SQ is an index which falls in that range. Okay. So, that is one candidate which can always be sent provided this thing holds. Okay. If this thing holds, then Q can send the packet SP. Why? Because in Q's window all packets in the range from AQ to SQ plus LQ minus 1 can be sent, and the SP numbered packet is one candidate which falls in this range. Now, either this or this has to be true. So, either P has a packet to send or Q has a packet to send, right. Either P has a packet to send or Q has a packet to send. Maybe both. It's or does not, it's not exclusive or, so both can be true. Alright. What does that prove? It proves that at no point can the protocol deadlock. So, it's either that P will have some packet to send or Q will have some packet to send. So, they will send. Now, see that those packets which can be sent are sent infinitely often, right. So, this packet SQ or this packet SP, which is a candidate for sending, will also be sent infinitely often, and we assume that the channel, in the channel, if a packet is sent infinitely often, it will eventually be received. Given packet, if it is sent infinitely often, will be eventually received. So, if the SQ packet is being sent infinitely often, it will be received. When it is received, then SQ will be incremented, right. Similarly, when the SP numbered packet is received, it will be SP will be incremented, right. So, either SP or SQ will be incremented also, because we can send them infinitely often and because they will be received infinitely often. So, the SP or the SQth packet will eventually reach and the SP or the SQth SP or SQ will increase, right, and this will continue to hold, and therefore, there will be continuous progress. Okay. That proves the correctness of the balanced sliding window protocol. Now, having gone through the theory of the protocol and looked at the correctness proof, let us first understand what is the implication of this window. Do we need a large window or a small window? Okay, what do we need? When are we going to use a small window? When are we going to use a large window? And how do we control the size of the windows? If we use a large value of LP and LQ, what does that mean? Right. So, if you have more, if you make LP and LQ large, that means you are allowing more number of packets to be transmitted before you receive your packets, right. Now, look at the trade-offs that we can make here. Okay. Suppose we say that okay, I will allow only one packet to be sent. When that is received, Q will send only one packet, then again P will send one packet. This is a case where we are only allowing one packet to be there in the network in the queue at a given point of time, right. Now, you see that when P is putting packets into the queue, okay, this queue, the communication network will take some time to route this packet to queue, right. It is going to take some time to traverse. Now, all that time both P or Q are remaining idle, right. On the other hand, what could have been done is that P, instead of sending one packet, pumps in several of them, right, and Q similarly pumps in several of them. And then the packets start moving towards each other, and when they are received, only then we say that only when after the when I will send 4 packets, when I receive the first packet from P from Q, then I will send the 5th packet. When I receive the second packet from Q, then I will send the next packet, and so on, right. You could decide like using a window of slightly larger size, right. Now, let us understand what are the trade-offs between these two. What is the difference between sending one packet at a time and sending several packets at a time? How does it affect the communication? Time. So, obviously this one is better in time. Why? Because P is not waiting, P is keeping on pumping packets and if we actually allow it to pump just that many number of packets such that when this packet reaches, then this packet is almost here, the first packet from Q is also almost here, then what is going to happen is in every time instant they will read a packet and write a packet. On the other hand, here if the communication delay is k, then they write a packet only every 2k, after every 2k time steps. Here they will write one packet every 1 time step, right. So, this is definitely faster, but we are forgetting one thing, we are forgetting the reliability. We can pump in a lot of packets, but they may not get received correctly. So, if there is congestion, then we need to use a smaller window. Why? Because you also have to retransmit the ones which were not received, right. And if you start pumping, if everybody starts pumping in lot of packets, then the network is going to get further congested. Now, you have heard of TCP, right? What is the full form of TCP? TCP stands for what is it? One person? What does it control? No, you are saying control. Flow control. How does it control flow?
By controlling the packet sending.
In what sense? How does it control the packet sending?
Number of sending delivered to the other side. Number of packet delivered to the other side. It controlling this one.
No, how?
Like in window size.
The window size is controlled. Okay. So, what TCP does is it uses an underlying sliding window protocol and it controls the size of the window. If the network congestion is high, then it will reduce the size of the window, and if it finds that the network bandwidth is better, then it will start slowly growing the size of the window. Okay. So, by controlling the window size, it is able to achieve better flow through the network. Okay. Now, just let me see. I think that is all about this thing. These are the results which we have already proved, and I think that is all that I had to say about this sliding window protocol. What I want you to do is, in the next lecture, I am going to look at routing algorithms. Okay, so in the next lecture, I will look at routing algorithms. Now, for this routing algorithms, I need you to do a little bit of background study. I need you to come prepared with the Floyd-Warshall algorithm. Okay, Floyd-Warshall algorithm for all pairs shortest path. Okay, all pairs shortest path in a graph using the Floyd-Warshall algorithm. So, please come prepared with that algorithm, and it will help you in the discussion. Okay, and you must understand the algorithm. I mean, it is not just that you read the algorithm and come, you must understand exactly how the algorithm works. Okay.